All right, we are on question number 17. This is a company must choose between two different projects. Project A has a 31% chance of profiting $2 million, a 60% chance of profiting $400,000, and a 9% chance of resulting in a loss of $200,000. Project B has a 24% chance of profiting $3 million, a 70% chance of profiting $200,000, and a 6% chance of resulting in a loss of $100,000. Calculate the expected value of each project based on the expected profit, which is the better project. Okay, so to calculate the expected profit, we need to set up like a probability distribution here. So I'm going to put my x over here, which is going to be the value, right? So actually, you know what? Let me call this project A. Sorry, that looks a little bit sloppy. Project A. And then my x here is going to be the value. And then the probability is going to be over here. So let's see. It says the value for project 31% chance of profiting $2 million. So 2 million. So it's a 2 with 6 zeros. $2 million and 31%, so 0.31. Then it says 60% chance of profiting $400,000. So 400,000, and that's a 60% chance. And then it says 9% chance of resulting in a loss. So negative 200,000. And that's 70%. So 0.70. All right. So, oh wait, sorry, did I write, hold on. I wrote the wrong one. I looked at the wrong thing. Sorry, 9% chance. Sorry, that's 0.9. 0.09. There we go. Okay, that looks better. Yeah, they should add up to 1, right? That's what tipped me off to the fact that I probably did that wrong. Because they didn't add up to 1. Okay, so in order to find the expected value, then I need to know what x times p is right here, right? So if I multiply 2 million times 0.31, I'm going to get 620,000. 400,000 times 0.6 is 240,000. And negative 200,000 times 0.09 is negative 18,000. So when I add all of those up, here the sum of the XPs, I get, let's see, what do I get? 842,000. Now that's positive, right? So if we add up, see, 620 and 240,000, let me put those commas there. That's 860 minus 18. Yeah, there we go. 842,000. So this is going to be their expected value, right? Expected profit, I guess. Now let's look at project B here. And let's calculate their expected value. Okay, so I think I may have put my line in the wrong place. All right, let's see here. It says Project B has a 24% chance of profiting $3 million. So $3 million. Okay, and that was 24%. And then 70% chance of 200,000. So 200,000, that's 0.70. And then a 6% chance resulting in a loss of negative 100,000. Okay. So x times p for this is going to be 720,000 here. And then 140,000 here. This is negative 6,000. Okay, so the total, the sum of the XPs is going to be For this one, $854,000. Okay, so the question says, okay, so this is, by the way, the expected value, also known as mu. Okay, this is same expected value, mu. Okay, which, based on the expected profit, which is the better project? Well, the expected profit is going to be higher for project B. So I would say project B has a higher expected profit, right? So project B has a higher expected profit. So, let's see, I have a little note here that says, remember that the expected value only has meaning if they can conduct many such projects. If they are only able to run one project, then they should choose the project according to the risks and rewards of just one project, not from the expected value. So, based on the expected profit, we would choose project B. But yes, this is the expected value, so in terms of, this would be in the, like in the long run, what we would expect to happen. Okay. So a company makes electronic gadgets. 1 out of every 50 gadgets is faulty, but the company doesn't know which ones are faulty until a buyer complains. Suppose the company makes a $3 profit on the sale of any working gadget, but suffers a loss of $80 for every faulty gadget because they have to repair the unit. Find the expected profit for the company, then estimate their total profit if they sell 150,000 gadgets. All right, so because it says that we need to find the expected profit, then that means we're going to be doing the expected value again, okay? So expected value, which is this, there we go. That formula right there. So just like we did on number 17. Now it says 1 out of every 50 gadgets is faulty. So let's make a little table here. So let me put here XP. All right. So we have two categories, right? We have faulty, working. All right. And so it says 1 out of every 50 gadgets is faulty. So 1 out of 50. Okay. And it says, but they don't know which ones are faulty until a buyer complains. Suppose the company makes a $3 profit on the sale of any working gadget. So the expected value on a working gadget is $3, and 49 out of 50 are going to be working because 1 out of 50 are not. And it says they suffer a loss of $80 for every faulty gadget. So that means negative 80 for that probability. Okay. And let's see. So find the expected profit. Okay, so we need to go over here and kind of multiply x times p. Well, negative 80 times 1 over 50 is going to be negative 1.6. And 3 times 49 over 50 is going to be 2.94. All right, so if we total those, what do we get? Well, we get 1.34. By the way, these up here were dollars as well. Okay. So the expected profit is going to be $1.34. So let me write that here. Expected profit equals $1.34. Now the question says, estimate their total profit if they sell 150,000 gadgets. Okay, well, if they expect to make $1.34 per gadget sold, then if we sell 150,000 gadgets, then they would expect to make, so total profit, okay, expected profit would be $1.34, which I guess I don't need the dollar sign here, times 150,000 gadgets. Well, when I multiply those together, I get $201,000. So this would be the total expected profit. This would be the expected value per gadget. So that's it for number 18. All right, let's see. Number 19. Which of the following is a binomial experiment? If an experiment is not binomial, specify which requirement failed. Okay, well, let's see here. It says, randomly interview 35 Americans asking if they voted in the prior election. Okay, so we have 4 requirements that need to be met. And one of them is that you have to have like a fixed number of trials, right? And so number of trials can be just the number of people that you're interviewing. So does this have a fixed number of trials? And the question is, yeah, or the answer is yes. N is going to equal 35 because that's the number of people you interviewed. Do we have, let's see, is the probability of success remain the same throughout? So probability of success remains constant. Let's see. So asking if they voted, well, I would say that that's a yes. Okay, we'll come back to that. Are they independent? Independent. The answer is yes. If you're randomly interviewing 35 people, 35 Americans, that's way less than 5% of the entire population, since there are like millions of Americans. So that's going to be a yes. And then the other one, only 2 outcomes. Only 2 outcomes. That would be a yes. It's either voted, didn't vote. Right? Those would be your 2 possible outcomes. Okay, let's come back to probability of success remains constant. Now, even though we don't know the probability of success, which is that they voted or they did not vote, that's going to remain a fixed number. So this is, I'm going to say yes here. Yes, this is binomial. So is binomial. It meets all the requirements. Okay. There we go. Letter B says randomly selecting 10 days out of the summer. Summer has approximately 92 days. And recording if the number of routine checkups was higher than 20 at the local veterinary clinic. Well, let's see. I don't know. Fixed number of trials. So they selected 10 days. So the fixed number of trials would be 10. So that would be okay. But let's see, probability of success remains constant. Don't know. Let me think about this for a minute. Now, independent, randomly selecting 10 days out of the summer. It has approximately 92 days. So we need to see if 10, so independent, I think, is our problem. Let's see here. So if n is equal to 10, but my total number of days is 92, right? So I want to know, is 10 divided by 0.05 less than or equal to 92? I'll put a question mark above that. So let's find out. What is 10 divided by 0.05? That's 200. Okay. So 200 is not less than 92. So not binomial because it's not independent. So that one fails there. Okay. Next. Randomly survey 50 traffic lights in a large city at 3 p.m. and record if the light was red, green, or yellow at that time. Okay, well, what are the is there only 2 outcomes? No. So only 2 outcomes. That would be no. There's red, green, yellow. So this is not binomial. Okay, I should have said no here. No, it's not independent. In a school district of 2,500 kids, randomly select 150 kids and survey if each rides the bus to school at least once per week. Okay, well, for this one, let's see. Let's check if it's independent. So fixed number of trials seems like that's a yes, right? 2,500. Probability of success remains constant. Yeah, I would say I guess so. Let's see. Randomly select 150 kids. So if we're taking, okay, here's our population. N, capital N is 2,500. Lowercase n is 150. Well, let's see. 150 divided by 0.05. Let's see what that equals. So 150 divided by 0.05. That's 3,000. Which is not less than 2,500. And therefore, independent is again a no. Independent is a no. And so this is not binomial. Okay. Randomly interview Americans until you find 50 that voted in the prior election. Well, this is not a fixed number of trials because you're randomly interviewing people until you find 50 that voted. So, fixed number of trials. That would be a no. So, not binomial. Okay. Number 20 says, answer the questions. The birth weight of children is normally distributed with a mean of 3.4 kilograms and a standard deviation of 0.6 kilograms. A pediatrician finds that the area under this normal curve to the left of 4 kilograms is 0.84. Give 3 different interpretations of this area. Okay, so the first interpretation we have here is that you can state this in terms of probability. So we could say 1. The probability of a random newborn having a birth weight less than, because it's to the left, right? So less than 4 kilograms is 0.84. So we would say less than because they said to the left, right? So to the left, that means less than. Okay. So that's one interpretation. The next one we can give in terms of like proportions. So we can say the population proportion or percentage of newborn children having a birth weight less than 4 kilograms is 0.84, or you could say 84%. Okay, so that's the second one. Once again, we're going to use less than here. Okay, and then our third interpretation is we could give in terms of percentiles. So a newborn child that weighs 4 kilograms is at the 84th percentile. Okay, because that means 84% are less than or equal to that child's weight. Okay, so those are our three interpretations for that one. Let's see. Letter B. The diastolic blood pressure of healthy dentists is normally distributed with a mean of 90 and a standard deviation of 4.5 millimeters of mercury. Okay. A doctor finds that the area under this normal curve to the right of 97 is 0.060. Give three different interpretations of this area. Okay, so this time it says we're going to the right. Area under the normal curve to the right. Okay, so number one, we could say the probability of randomly selecting a dentist having a diastolic blood pressure more than 97 mmHg is 0.060. Okay, that would be, oh, we don't have to put the 0 on the end of it, I guess. That's just the way they stated it. We could just state that. Okay, the second one we could say is the population proportion or percentage of dentists having a diastolic blood pressure of more than 97 mmHg is 0.06 6%. Okay. Then the third, of course, you give percentiles. Now this time, though, we're saying that 6% are higher, right? And so what that means is that you would be at the 94th percentile. So a dentist having a diastolic blood pressure of 97 is at the 94th percentile. Okay. So To the right means more than. And if you're doing percentile, then you're going to have to do 100 minus whatever your percentage is there. Okay, number 21. Gus the cat uses his right paw 85% of the times that he only uses one paw to achieve his goal. Find the mean and standard deviation for the number of times Gus uses his right paw in random samples of 40 one-paw actions. In random samples of 40 one-paw actions, what outcomes would be considered usual? Okay, well, let's see here. I think this is a binomial thing, right? Let's see. Are there a fixed number of trials? Yes, we have random samples of 40 one-paw actions. And we want to know if if the probability of success is fixed or remains constant. And the answer is yes. It says 85% of the time that he uses his right paw, so that's fixed. Are there, let's see, is this independent? I would say yes. The random samples here. And then the other thing we need to check is to make sure that there's only two possible outcomes. He either uses his right paw or he does not. So I will say that yes, this is binomial. So make a little note here. This is binomial. Okay, so since this is binomial, let's see, what are our variables here? Well, we have the probability of success here, our P, is going to be 0.85 because success is using the right paw. And our N is 40. This is the number of samples we're looking at here. So we want to know, find the mean and standard deviation. So since this is binomial, the mean is just NP. Okay, so the mean here is 40 times 0.85, which is equal to 34. Okay, and then our standard deviation is the square root of NPQ. Well, my N is 40, my P is 0.85, and my Q is just 1 minus P. So I'll just put 1 minus 0.85, like that. Okay? So if I multiply all of that, take the square root, my standard deviation is 2.3. Okay? Now it says what we need to find after this is we've got the mean and the standard deviation. So let me put here mu equals 34. And we want to know, in random samples of 40 one-paw actions, what outcomes would be considered usual? Well, we need to figure out what's 2 standard deviations away from the mean, right? So I need to know what is mu minus 2 sigma and what is mu plus 2 sigma. Well, mu minus 2 sigma is 34 minus 2 times 2.3, which equals 29.4. And then mu plus 2 sigma, 34 plus 2 times 2.3 would be 38.6. Okay, so let's draw a little picture here, right? Okay, so we've got our mean here. Here is mu minus 2 sigma. This is mu plus 2 sigma, right? Now, I'm going to put actual numbers here. This number is 29.4. This number is 38.6. So anything in between, these are considered usual. Anything outside that is considered unusual. Oh no. Oh goodness. All right, forget that. Oh gosh, okay. How about that? Why can't I make this thing straight? Oh my gosh. Y'all, I don't understand why I can't. Okay, there we go. Perfect. Just not touch it now. Okay. All right, so the numbers between here, and this is considered the usual range. This would be unusual, right? Unusual. So what numbers are between here? Well, we have, let's see, 30 up to 38. So 30 to 38. So in between 30 and 38, those are going to be considered usual. And then anything beyond that would be considered unusual. So any outcome from 30 to 38 is usual. Okay, so we got that answered. The mean is answered. The standard deviation is answered. Okay. Let's see. Number 22 says, describe the distribution or sampling distribution. Be certain to check your requirements. Number 22. GE manufactures a decorative clear 60-watt light bulb that it advertises will last 1,500 hours. Suppose the lifetimes of the bulbs are approximately normally distributed. Okay, let me just highlight that. Approximately normally distributed with a mean of 1,550 hours and a standard deviation of 57 hours. A customer wishes to know what percentage of the light bulbs will last less than the advertised time. What distribution should the customer use to calculate the percentage? Specify all necessary information for this distribution. Is this distribution bell-shaped? Well, I would say it is bell-shaped. I mean, it tells me that it's approximately normally distributed. So, let's see. What would we say here? Customer wishes to know the percentage of light bulbs. What distribution should the customer use? Okay, so we're not actually calculating anything. It just says, what distribution should the customer use to calculate the percentage? Well, because it says normally, it says, okay, so the problem says normally distributed. So use normal distribution. Okay. And so use normal distribution with mu equal to 1,550 and standard deviation equals 57. This is bell-shaped because it's so yeah, is the distribution bell-shaped? Yes. Yes. The distribution is bell-shaped. Okay. Next. All right. From these light bulbs, GE Quality Control randomly selects 10 bulbs. They wish to know the probability that the mean lifetime for the 10 bulbs will be at most 1,500 hours, the advertised time. Describe the sampling distribution for the sample means. Is the sampling distribution bell-shaped? Well, the sampling distribution, let's see. It says the question is about a random sample. We must check the requirements for means. The selections were random. The sample did come from normally distributed population. So let's see here. What's our sample size? N equals 10. So we want to find if n divided by 0.05 is less than our entire population, right? So 10 divided by 0.05 is 200. And so the population of all light bulbs, this is definitely like less than or equal to all light bulbs. So let's see. Okay, we got that one requirement there. Let's see. What's another requirement that we need? Population standard deviation is known. So sigma is known. Okay. So we are talking about the mean lifetime of light bulbs. So when you see that it's like the mean lifetime, right, of a group, and it's under normal distributions, we're talking about the sampling distribution. So we need to use the chapter 8 formulas. So what we would say is we would use the normal distribution with mu equal to 1550, but our standard deviation, we would do what was it, 57, right? But you would put over the square root of 10. So you guys remember that? We'll read that from chapter 8 for the sampling distributions. So this is for the sampling distributions. That's because it talks about the mean lifetime. So this is what you would put in your calculator. But if you wanted to, give a number, that would be 18.024983. Okay. And of course, these are hours. So is the sampling distribution bell-shaped? Yes. The sampling distribution is bell-shaped, and that's because the original because the population was normally distributed too. So because the population was normally distributed, which was bell-shaped, then the sampling distribution would also be bell-shaped. Okay. Let's see here. What is big letter B say? According to the U.S. National Center for Health Statistics, there's a 98% chance that a 20-year-old male will survive to the age of 30. An actuary needs to find the probability that at least 248 survive to the age of 30 in a random sample of 250 20-year-old males. What distribution should the actuary use to calculate the probability? Specify all necessary information for this distribution. Is the distribution bell-shaped? Okay, so let's see here. What are we trying to do? Well, what do they give us? There's a chance of survival, and then we have a number of people here. So we know that P is 0.98. That's the probability of quote-unquote success, which is our survival. And I know N, my sample size, is 250. This is seeming kind of binomial, because I've got the probability of success, which is survival, and I've got the sample size, N, which is 250. So I'm kind of thinking maybe binomial. So surviving So we've got two possible outcomes. You either survive or you don't, right? I have a fixed number of trials because I have 250 people. So independent. So my N, 250. If I divide that by 0.05, let's see here. 250 divided by 0.05, 5,000. I would say that's less than the population of all 30-year-old males. I'm sorry, 20-year-old males. And so the other thing is, so we have two outcomes, fixed number of trials, independent, probability of success remains constant. Yeah, this is binomial. So this is binomial. So we would use the binomial distribution. Okay, so use binomial distribution here. And with these two things, with P equals 0.98 and N equals to 250. That looks super sloppy. Okay. To know if a binomial is bell-shaped or not, we need to check the value of N times P times Q. So we need to see if N times P times Q is, if it's greater than or equal to 10, then it is bell-shaped. So let's see what we get here. N times P times Q. 250 times 0.98 times 0.02, that's Q. Well, this is 4.9, which is less than 10. So this is not bell-shaped. Okay. The actuary calculates that the probability that at least 248 survive to the age of 30 in a random sample of 250 20-year-old males is 0.122. Would it be unusual for at least 248 to survive to the age of 30? Well, let's see. Is 0.122, this is greater than 0.05, right? So this would be not unusual. I guess that's all we need to do there, right? Just compare. Okay. Since it's not bell-shaped, we can't use the mu minus 2 sigma, mu plus 2 sigma. That's only if it's bell-shaped to determine if it's unusual or not. All right. So in letter C, a particular cicada species has a mean lifespan of 16 years with a standard deviation of 1.2 years. A random sample of 50 of these herbivorous bugs was kept in a museum, and they had a mean lifespan of 17 years. The museum wishes to find the probability that such a random sample of this cicada species would have a mean lifespan of 17 or more years. Describe the sampling distribution for the sample means. Is the sampling distribution bell-shaped? Okay. So, let's see. What do we have here? What information do we have? Describe the sampling distribution. Museum wishes to find the probability such a random sample of the cicada would have a mean lifespan. Okay, so I see that it says a mean lifespan of 17 or more. So to me, that tells me we're talking about the sampling distribution. So let's check our requirements. So it's about a random sample of 50 and the sample's mean. So we need to check the requirements for means. The sample is said to be random, so that's number one, right? Is it random? Random. Yes. And then we also need to check to see if our sample size is greater than or equal to 30. So is n greater than or equal to 30? Yes, because 50 is greater than or equal to 30. Stated. Whoops. Yeah, stated. Okay, and then the third thing, we need to know if n divided by 0.05 is less than or equal to n. So let's find out. What's my lowercase n? 50 divided by 0.05. So 50 divided by 0.05 is 1,000. Okay, but this is 1,000. So less than or equal to all cicadas. Yeah, I think we're going to go with, that's fine. Yeah, that's going to be a yes. Okay. So the population standard deviation is also known. This is known. Okay. So we can use the normal distribution. But since we're using the normal distribution for the sample means, we must use the sigma over the square root of n. So we can use the normal distribution. Normal distribution. With mu equals, what's mu? 16, mean lifespan is 16 years. And the standard deviation equals sigma, so 1.2 divided by the square root of n, which is 50. Okay. And we can give this as a decimal, would be 0.169706. I'm going to just rewrite this. There we go. All right. The museum calculates this probability using a computer and receives the output 1.9. This is P 1.9013 E -9. Has something unusual occurred? Well, this probability, if we were to write this out as a decimal here, this is going to be 1, 2, 3, 4, 5, 6, 7, 8. 2-ish. That's the probability, right? So if you're gonna compare that is way less than 0.05. So definitely unusual. So something very unusual has occurred, but we conclude that the mean lifespan of these bugs in captivity is longer than the lifespan for these bugs in general. So, I mean, they're living in a controlled environment, so obviously their lifespan will probably be longer, given that they're not going to have any predators or anything like that in this controlled environment. So, yes, very unusual there.